When the war finally ended, silence settled over the workshops. The echo of engines, once constant, was gone. But in one hangar on the outskirts of London, the noise began again. Only this time, it wasn't the sound of a tank rolling into battle. It was the hiss of a cutting torch. British engineers stood around a captured German Panther tank. Its armor was pitted and scorched, its paint still carrying the smell of war. But they weren't here to admire it. They were here to take it apart, piece by piece. The Panther had terrified Allied crews across Europe. It could punch through a Sherman at over a mile, its armor angled like nothing else on the battlefield, but it also broke down. A lot. Engines seized, gearboxes failed, crews abandoned them by the roadside. No one could understand why a machine built with such precision kept dying on its own. So in late 1945, the British decided to find out. They brought several Panthers home, burned, broken, but mostly intact. And inside one of them, a team from the Royal Electrical and Mechanical Engineers focused on a very specific mystery: the final drive. It was the heart of the Panther's motion, the system that transferred engine power to the tracks. In theory, it should have been one of the strongest parts of the vehicle, but battlefield reports told a different story. Most Panthers lost mobility after only a few dozen miles. Something was killing them from the inside. The engineers didn't trust the German manuals. They were full of contradictions and optimism, so they did what engineers do best. They opened it up. What they found inside the first unit shocked them. The gears weren't destroyed by enemy fire. They were shredded from within. They ran their fingers along the steel edges, sharp, uneven. The teeth didn't look worn. They looked torn apart. One of the men, Major Hales, a veteran mechanic from the Normandy campaign, said quietly, "This wasn't bad luck. This was built to fail." They didn't understand what he meant yet. But over the next few weeks, in a dimly lit test bay filled with oil fumes and chalk notes on the walls, they would uncover a design flaw so fundamental. It explained why one of the most feared tanks of World War II was often left stranded in mud, powerless to fight. And it all started with a single, almost invisible detail: a tiny miscalculation buried deep inside the steel. By 1945, Allied engineers were obsessed with understanding German machinery. The war had proven that the enemy's designs were decades ahead in some areas and disastrously overcomplicated in others. The Panther represented both extremes. Its gun, optics, and suspension were revolutionary, but its mechanical reliability was catastrophic. Reports from the field showed a pattern. Panthers weren't being knocked out by enemy fire nearly as often as they were being immobilized by their own systems. Transmission failures, overheating, loss of steering, all pointing to something in the powertrain. The Ministry of Supply decided to get hands-on. Several captured tanks from France and Belgium were shipped to the School of Tank Technology in Chertsey and to the Royal Arsenal at Woolwich. Each would be stripped, tested, and catalogued. The focus soon narrowed. The final drive, the heavy gearbox that sent power from the transmission to the tracks, was failing more often than any other part of the vehicle. At first, the team assumed it was a materials problem. Germany, near the end of the war, was short on quality steel. Maybe they'd cut corners. Maybe the alloy was impure. But the lab results told a stranger story. The gears were high-grade steel, better than what the British used on their Cromwells. The hardening process was textbook. The tolerances, though, weren't. The engineers ran the parts through micrometers and hardness tests, writing numbers in grease pencil on the bench. Something wasn't adding up. The steel was strong enough to survive, but the system wasn't surviving. Why? To answer that, they reassembled the unit on a rig, a makeshift test stand built from spare tank parts and a dynamometer. They powered it up slowly, watching the gauges climb, and at exactly 1,800 revolutions per minute, they heard it. A dry, metallic scream, then silence. The machine locked up. When they opened it again, the teeth were gone. Torn, not worn, sheared by torque far below the rated limit. The chief engineer leaned over the bench, flashlight trembling slightly in his hand, and said, "Something's wrong in the geometry." He was right. And what they discovered next would rewrite what they thought they knew about German precision. The next morning, the test bay smelled of burnt oil and metal dust. The Panther's final drive sat on the bench like a wounded heart. Its gears twisted, its bearings collapsed. Every tooth that should have meshed smoothly was chewed away, almost liquefied at the edges. Major Hales leaned in, running a gloved finger across the broken gear. The metal left a gray streak on his fingertip. "This," he said quietly, "shouldn't happen under that load." They checked the torque chart again. The numbers didn't lie. The gearbox had failed at just over 2,000 Newton meters, barely half of what the manual claimed it could handle. At first they suspected a heat treatment problem. Maybe the Germans had hardened the surface too deep, making it brittle. But when they etched a sample and looked at the grain under a microscope, it told a different story. The grain was perfect, fine, uniform, beautifully tempered. This was good steel. So if the metal wasn't at fault, the failure had to be mechanical. The chief engineer ordered the pieces cleaned and reassembled, not to run, but to study. The teeth didn't fit the way they should. Each pair meshed slightly off-center. Under load, that meant enormous stress at the tip of every gear tooth. A young technician, Corporal Jenkins, fresh from the REMI school, took a set of calipers and measured the offset. "Sir, they're not symmetrical," he said. "Left side is 2/10 out." 2/10 of a millimeter, barely visible to the eye, but at high RPM, that was enough to rip the surface layer apart. They marked the contact points with engineer's blue, rotated the assembly by hand, and watched the pattern appear. The contact wasn't spread evenly. It was hammering one edge again and again. That's when they realized the flaw wasn't from wartime production shortcuts. It was in the design itself. For years, Allied engineers had admired German tolerance charts. The myth was that German machines were perfect, built to microscopic precision. But perfection, it turned out, could be lethal. The Panther's designers had pursued efficiency so aggressively that they'd left no margin for forgiveness. Its gears were cut to such tight tolerances that a fraction of deformation under load, any flex in the shaft or housing, threw the system out of alignment. The steel didn't bend, it fractured. When the British compared it with the final drive from a Sherman, the difference was obvious. The American part looked crude, almost agricultural. The machining marks were visible, but it ran longer, survived shocks, and could be repaired in the field. The Panther's was beautiful and fragile. Inside the lab, they mounted a fresh unit and applied dye to the housings to check for strain. Within minutes of testing, hairline cracks appeared around the bearing seats. The engineers exchanged glances. They weren't seeing wear. They were watching the casing itself breathe under stress. One of them, a veteran of pre-war Rolls-Royce projects, muttered, "They built a racing car for a battlefield." But the investigation wasn't over. If tight tolerances were the root, what pushed them over the edge? They started examining the lubrication system. The Panther used a complex arrangement of oil galleries meant to keep every tooth bathed in lubricant. But when the British pumped fluid through at normal operating pressure, only half the channels flowed. The rest were blocked, clogged with hardened grease and microscopic flakes of bronze. Wartime crews had reported constant leaks and overheating. Now it made sense. Poor sealing let dust and grit in. Heat thickened the oil. The precision gears, already dancing on a knife edge, seized. They heated the casing with a torch and watched the residue melt. A smell of scorched lubricant filled the room. Hales turned away, coughing. "It's not just the steel," he said. "It's the environment. Mud, grit, bad oil. The battlefield killed the precision. The Germans had designed a masterpiece for perfect conditions. The battlefield had no perfection. By week's end, the British had run 3 more tests. All failed the same way. No 2 units survived longer than 25 hours under simulated combat load. The engineers filled a report folder. Panther Final Drive Examination, report number 1246. Inside, next to the torque curves and photos of shattered gears, someone scribbled a line in pencil. The enemy did not lose this tank to us. They lost it to themselves. But for the lead engineer, the question still lingered. Why had such brilliant designers overlooked something so simple? Pride? Pressure? Or a belief that more precision always meant more strength? He wasn't sure. Yet the answer would come from an unexpected place. A late-war German memo that crossed his desk 2 weeks later, stamped Geheim Technische Abteilung, 1944. Inside, it described a desperate attempt to fix the Panther's reliability by replacing the final drive entirely. And the reason it never happened would reveal the real killer behind one of WWII's most feared machines. 2 weeks later, the chief engineer received a brown envelope from the intelligence office. Inside was a translated German document, yellowed, fragile, but clearly marked with the word Geheim. It was dated late 1944, signed by an engineer from MAN, one of the factories that built the Panther. The document outlined a proposed redesign of the final drive, larger bearings, revised gear ratios, and a shift from precision ground teeth to slightly wider, more forgiving cuts. In the margin, the note read, "Production cannot accommodate change, resources insufficient. Continue existing model until further notice." The engineer reading it exhaled slowly. The Germans had known. They had identified the flaw months before the Allies ever examined it. But the factories were collapsing under bombing raids, material shortages were critical, and the Reich's leadership demanded quantity over quality. There was no time to fix perfection. They had been forced to build failure into every tank that left the assembly line. As the British team processed the memo, the realization spread through the workshop. The Panther hadn't been destroyed by Allied firepower or by engineering ignorance. It had been destroyed by its own war economy. The pressure to maintain output had frozen innovation. Every field unit that complained about seized drives was ignored, because admitting the flaw would have slowed production. Pride and bureaucracy had done what no anti-tank gun could do. The Panther was the victim of its own myth, that German precision was untouchable. The engineers decided to replicate the Germans' proposed fix. Using spare materials, they remachined one final drive with slightly looser tolerances and reinforced bearings. When they ran the test again, the result was almost unbelievable. The unit lasted more than 80 hours under full load, more than triple the lifespan of any previous run. There was no metallic scream, no sudden lockup, just the rhythmic hum of machinery that finally worked the way it should have from the beginning. It proved what the memo had implied. The problem was never in the concept. It was in the obsession with flawlessness. By the time the tests ended, the Panther carcass in the corner was little more than a skeleton. The team stood in silence, watching oil drip from the rig, the faint ticking of cooling metal echoing like a clock. Hales closed the report folder and wrote the final line himself. "Overdesigned, understood too late." That phrase would appear years later in a Ministry of Defense briefing on foreign armor. It became the quiet lesson of the Panther investigation. That engineering brilliance, without room for imperfection, will always collapse under its own weight. The captured drives were eventually scrapped. The report was filed away under Engineering Intelligence, confidential, forgotten among stacks of other post-war analyses. But decades later, when historians rediscovered those pages, they realized how close the Allies had come to learning a principle that still defines modern design: that reliability often hides in simplicity. The Panther's gears, cut with surgical precision, had destroyed themselves because the battlefield is not a laboratory. Mud, vibration, temperature, and chaos punish perfection more than flaws. Standing in that dim workshop, the British engineers hadn't just dissected a machine, they'd dissected a philosophy. The Panther was proof that even the most formidable war machine can fall, not to its enemy, but to the smallest numbers on a drawing board. And the echo of that lesson, hidden in a folder labeled 1246, still whispers through every engineer's workshop today. If this dossier earned your curiosity, tap like and subscribe to WarTech Dossiers. There's another case file waiting on your screen right now. Open it before the trail goes cold.